Alright, so we wound up here with this Laplace transform table. What we really need to look at, honestly, is these properties here. There's some very important properties here, which we're going to talk about in this lesson here. And these are all very useful for analyzing Laplace transform, analyzing circuits with Laplace transforms. Some are going to be used more frequently than others, but they're all very useful ones. So the first one here on that table, which I'm not going to really go into in detail, is what we call is the linear properties. That just basically means that if you have a1 f at t plus a2, I should say f1 at t, f2 at t, that this, doing a Laplace transform of this, so I'll put an L for Laplace transform, is just a1 capital F1 at s plus a2 capital F2 at s. And to see this in work, just real quickly to see how this works as an example here, if we had a signal s at t being 3 u at t minus 5 delta at t, then capital S at f, just using my Laplace transform table, would just be 3 over s minus 5 times 1, which is just 5. So 3 over s minus 5. That's basically what the linear property says, is that you just look at, oh, Laplace transform u at t is 1 over s, Laplace transform of delta is 1, and we're done. Which of course is a very useful property to have. Linear properties are very useful. Then there's some of these scalings and time shifts here, which we will talk about in a second, but the one I want to talk about next is what's called the time differentiation here. So we want to look at, because this is actually going to be useful for when we're trying to do circuit analysis, because we have derivatives in our voltage and current relationships for capacitors and inductors. So the question is, what happens when you take a derivative of a function and you want to do the Laplace transform of that? What is that equal to? Well, it sounds a little weird, but what we're going to do is we're going to do exactly what it's saying. We're going to do the integral from 0 to infinity of the derivative of f at t e to the minus st, because that's just the definition of a Laplace transform. Now, this is where things get a little interesting, I think, because basically you're saying, oh wait, you take a derivative, you're doing an integral of a derivative, they cancel each other out. Well, not exactly, because it's just the derivative of f at t, then that's getting multiplied by e, then you're integrating. So you don't get this integral canceling derivative business out. But there is a way to approach this, and this is integration by parts. So who thought that integration by parts would come back again? And remember, integration by parts is that if you have u dv, this is equal to uv minus v du. Okay, so if we do this here, we wind up with, what you do is you do u is equal to e to the minus st, which means du is simply going to be negative s e to the negative st. And then we let dv be this derivative of the function. So by doing integration by parts, we are separating these out, because remember, there's a, I don't hit this. There is a multiplication right here. But what we're saying is, okay, yeah, we're recognizing that multiplication, we're letting this be u, and we're letting this be dv. But then, if I integrate this, well, now this is just a derivative, and if I integrate a derivative, I do get back just f at t. All right, so what do we wind up here with? Well, we have u times v, so we have e to the minus st f at t 0 to infinity minus the integral from 0 to infinity of negative s e to the negative st times f at t dt. So let's clean this up a little bit. First off, I'm going to have to evaluate this. So this is e to the negative infinity f at infinity minus e to the 0 f at 0 this would then be plus, because I got a negative negative, I'm going to pull the s out, integral from 0 to infinity f at t e to the minus st dt. But what we end up getting here is, well, this is going to go to 0. Now, we technically don't know what f at infinity is going to go to. So we could run into some problem, but we'll just make the assumption here that this is bounded so that it doesn't go off to infinity, or that if it, I won't say bounded, that even if it goes off to infinity, basically that the exponential function is going to have a higher growth rate than the f at infinity. So we're just going to say this whole term here goes to 0. Now we have made an assumption, we've put a restriction on the function f, but with the functions we're going to be dealing with, sine, cosine, u at t, e to the negative at, things like that, those assumptions are fine. We already know that that's going to be okay with what we're doing. And then of course e to the 0 is just 1, but f at 0, we don't know what that is. That's an initial condition. But then look at this here. Integral from 0 to infinity f at t e to the minus st. This is just the definition of the Laplace transform of f at s. So this is the key thing here. Star this. The Laplace transform of the derivative is equal to s capital F at s minus f at 0 minus. And this is my initial condition. Now the initial condition might be 0, but it might not be 0. Now we can extend this. I'm not going to do the proof of this, but we can extend this to higher order derivatives. For instance, the second derivative. Now, you just have to do integration by parts twice. Now, I'm not going to do that, but what you'd wind up with s squared f at s minus s f at 0 minus f prime at 0 minus. So we have two initial conditions now. Now, I'm going to write one more down here, and as I'm writing this down, you should think in your head what the answer should be. You should be able to see the pattern at this point and know what the answer of this is going to be. It's going to be s cubed f at s minus s squared f at 0 minus s f prime at 0 minus f double prime at 0 minus. And we can continue the pattern on forever. Now we're not going to really need that high of order derivatives, but we could still move on and do those as well. Okay, so let's go back to this table. So we've got this linearity, and then look, we've got all these time differentiations going on here. And it has even, kind of, well, hey, if you want to go on forever, this is the pattern, to follow. Alright, there are a couple other ones that are going to be useful to us. Another property here is when you do an integral. So if you look at the Laplace transform, of the integral from 0 to t, and then I do f at x dx. Now I'm not going to prove any more of these, but I'm just going to write down the results here. This is 1 over s capital F at s. Which is right here, this time integration. And again, why do we want to be able to do an integral? Well, some of the current voltage relationships for capacitors and inductors involve integrals. So I want to be able to do that integral. Now, the other important ones on this table here are the time shift and what's called also the frequency shift here. So the time shift is the one that we're going to look at here. There are some other ones here like frequency differentiation, frequency integration, initial and final value. The initial and final value, these are actually extremely important. And maybe I'll go ahead and write them down here because those are pretty easy to show, but we'll see them in signals and systems again. But the time shift one is actually very useful to us. So that's saying that if you have the Laplace transform if I can write the L again, Laplace transform of f at t minus a, u at t minus a. So we're doing a time shift here. This is just equal to, or not equal to, yeah, this is equal to e to the minus as capital F at s. So we really just get this factor here. This is what I would call is my time shift factor. Alright, so these are kind of some of the important properties. There are other ones on the table here, as I said, that you might want to use depending on the problem. And when we need these properties, if we haven't discussed them, we'll obviously discuss them in the problems. But the most important ones, again, are the time differentiation, the time integration, and the time shift, as well as the linearity.